Now, let's tackle the issue of solving a system of equations. We are going to use the elimination method. The elimination method is essentially based on two key ideas, two rules. Linear combinations of equations, so you are allowed to linear combine equations, meaning you multiply equations by numbers and then you sum them, the first thing. And the second rule is back substitution. Well, let's see with the example exactly what these two rules mean. You'll find here a 2 by 2 system, two equations with two unknowns x, y. So what I'm going to do, well, I'm essentially substituting the second equation, the L2 equation that you find here, by the equation itself minus twice the first equation. So this is the idea. You have the second equation, you have the first, you multiply the first by minus 2, and then you sum the two equations. And the result of this summation is your new second equation. This is what you find here. Can you see? If you multiply the first equation by 2, you get here 2x minus 8 is equal to minus 4, and then you sum. So 2x minus 2x gets you 0, minus 6 plus 8 is 2, and finally 5 minus 4 is 1. So what you find here is your new, the L2 prime for new, the new second equation, which is equivalent to the original one. The key idea is that this old system of two equations and the new system are equivalent. They have the same solution. And the reason is that I'm adding the same number to both sides. Why did I do such a linear combination? Notice, here the second equation has two variables. Here it no longer has two variables. It only has just one, because this is 0 here. So it's 2y is equal to 1. So from this linear combination, this special choice of linear combination, I was able to eliminate one of the variables on one of these equations. And that's good, because the less variables I have in my system, the easier it is to solve. Now, let's continue solving our system of equations. This is our original system here. This is the first linear combination that we did, which eliminated our 2x, now it's 0. Now the next step is I'm going to divide the second equation by 2. So I'm dividing the left side and the right side by 2. So I get just y is equal to minus 1f. Downstairs you have here the system under the matrix vector notation. So this corresponds to this corresponds to this, and this corresponds to that. Now it's 0 here. 1y is equal to, let's keep pushing this to the side, to 2 1f, this right hand side. My goal now is simply to eliminate this entry here, or this variable here. Again, I want to do linear combinations to make disappear as much as possible the variables in the equation. So if I do that, how do I do that? Well, if I multiply the second equation by 4 and then I sum to the first equation, well, you get 4y minus 4y, which is 0, so it disappears. So the new first equation, L1 prime, is the old L1, this one, plus 4 times L2. Downstairs we find again the matrix vector notation. From here we have this, so we have this one, you want to eliminate the minus 4, you do this linear combination, you get the 0. After we arrive at this stage, well, the solution is obvious. X must be chosen to be equal to 4, and y must be chosen so that is equal to 1f. Now you can understand what do I mean by the elimination method. You are eliminating variables as much as possible from our equation. In particular, how do I know which variables to eliminate? We start by what's called the pivot variables, or the pivot entries. Here, the 1, for example. So you want to use this 1 here to eliminate what's downstairs. This is what guides me for this linear combination. I want to eliminate what's downstairs. Then I try to eliminate upstairs. This is the second pivot. This is the first. This is the second. I want to use the second to eliminate this one here, this entry. This is what I did here with this linear combination. And so on. You get now the identity matrix, which essentially means, so x times 1 is x, y times 1 is y. So y is equal to the 4 1/2 vector here.